Creating Thevenin voltage sources. Let's start off with an example of a Thevenin voltage divider. And this assumes that you've read the chapter on a Thevenin equivalent circuit and even done the examples that the book has laid out for you. But I like to do this example because you're very familiar with a voltage divider. So what's the first thing we do when we Thevenize a circuit? We find the open circuit voltage between nodes A and B, from between here and here. And what this means, open circuit voltage, is not that this is open circuit or this resistor's open circuit or this resistor's open circuit, but that there's no RL or resistive load between A and B. And so if we look at that, what is the voltage from A to B? We can see that it's simply the voltage divider equation. So we get the Thevenin voltage is equal to the voltage divider equation. That's easy enough. Then we find the equivalent R Thevenin between A and B by setting all the independent voltages and current sources to 0. So that in order to set this voltage to 0, we replace V1 with a wire of 0 resistance. And then we have to notice something, that resistor 1 and 2 both have one side connected to node A, and the other side of R1 is connected to node B, and the other side of R2 is connected to B. So if this is the definition of being in parallel, and if I rotate this R1 down to here and get this shape, then it's even more easy to recognize that R1 and R2 are in parallel. And so the Thevenin equivalent resistance is R1 in parallel with R2. And so we can go from this circuit to this circuit, and they're equivalent. Now, let's do another example where an ideal voltage source has no series resistance. And we'll see that that can cause a bit of a trouble for us. The open circuit voltage, though, equals the Thevenin voltage and can be found by inspection because R2, R1, and V1 are all connected in parallel because one side of R2, one side of R1, and one side of V are connected to the A line, and the other side of these devices are connected to the B node. That means they're in parallel. And so the voltage across here is the same as the voltage across here is the same as the voltage across here. So the threshold, the Thevenin voltage is equal to V1. But let's notice what happens when we try to find R Thevenin. We replace this voltage source with a wire, but now notice A is on the same wire as B, and that means they're connected or shorted. And so if I looked at the Thevenin equivalent resistance, it would be 0. And so I would have the V Thevenin voltage of V1, and then I would have R Thevenin as 0. But this circuit and this circuit are supposed to be equivalent, and something with 0 resistance here is certainly not something with R1 and R2 here. So it just doesn't work. So if your R Thevenin is 0, it's not an equivalent circuit. You've lost the information that R1 and R2 are there. Let's do a current source example. Here we have a current source flowing, sourcing a current through R1 and R2. And what's VAB? Well, it's the current going through the parallel combination of R1 and R2. So it's I1 through the parallel combination. Then how do we find the equivalent Thevenin resistance? Well, how do we set a current source to 0? We take it out of the circuit. Now when I look at it, this node is disconnected. R1 and R2 can be easily recognized as being in parallel. And so R Thevenin is R1 times R2 divided by the sum of R1 and R2. Now let's do a little more tricky example. Let's find R Thevenin and V Thevenin with a dependent current source. And so, as we've seen before, this is a simplified transistor model. And I want the open circuit voltage between A and B, and that's going to be V Thevenin. And there's going to be no RL between nodes A and B. So, from a previous class, V out equals Vs times GM times R out. And so the Thevenin voltage is minus GM Vs R out. Now let's find the Thevenin resistance. So we replace V1 with a zero resistance wire. Well, now the node G is shorted to node B. So it's shorted. So G has to be 0 volts. Well, if G is 0 volts, then the current is 0 volts. How do we get rid of a 0 amps, excuse me. How do we get rid of a current source that's at 0 amps? We remove it from the circuit. And then by inspection, our Thevenin is just R out. And so putting it all together, this Thevenized transistor is equivalent to this. V Thevenin is minus GM Vs R out, and R Thevenin is equal to R out.